For millennia, landslides have been a part of Earth's ever-changing landscape. Long before the advent of modern science, ancient civilizations bore witness to the destructive power of these natural disasters. From the towering Himalayas to the rugged Andes, landslides have shaped civilizations and left an indelible mark on human history. Ancient cultures often attributed landslides to supernatural forces. Myths and legends emerged, offering explanations for these seemingly inexplicable events. In ancient China, landslides were seen as expressions of anger from the spirits of mountains. Offerings and rituals were performed to appease these powerful entities and ward off future disasters. Similarly, indigenous communities in the Americas developed rich oral traditions about landslides, often associating them with stories of creation or destruction. These tales, passed down through generations, served as cautionary reminders of the power of nature. While ancient explanations for landslides may seem quaint today, they reflect a deep respect for the natural world. These early observations, though lacking a scientific framework, represent the earliest attempts to understand and cope with the threat of landslides. By recognizing patterns in landslide occurrences, ancient communities learned to identify hazardous areas and adapt their practices accordingly. The legacy of these ancient encounters with landslides can still be seen in the cultural memory of many communities around the world. These stories and traditions serve as a reminder of the long-standing relationship between humans and landslides, a relationship that continues to shape our understanding of these dynamic events. The scientific study of landslides emerged gradually, intertwined with the development of geology and engineering. Early naturalists and geologists, driven by curiosity and a desire to understand Earth's processes, began to document and analyze landslide events. These pioneers laid the foundation for the field of landslide science. One of the earliest recorded attempts to systematically study landslides came in the 18th century with the work of Swiss naturalist Horace Benedict de Saussure. Saussure, known for his pioneering work in the Alps, meticulously documented landslides and avalanches, recognizing the role of factors like slope angle and water saturation in their occurrence. His observations, published in his influential book Voyages dans les Alpes, marked an important step towards a more scientific understanding of landslides. The 19th century witnessed further progress in landslide studies. Geologists began to develop theories about the forces that drive landslides, linking them to processes such as erosion, weathering, and tectonic activity. The invention of photography in the mid-1800s provided a powerful new tool for documenting and analyzing landslides, allowing scientists to study these events in greater detail than ever before. As industrialization gained momentum in the late 19th and early 20th centuries, the demand for infrastructure, such as roads, railways, and dams, brought about new challenges related to landslides. Engineers began to develop methods to assess landslide hazards and design structures that could withstand the forces of these natural disasters. This period saw the emergence of soil mechanics as a distinct field of study, providing crucial insights into the behavior of soil and rock on slopes. The ability to visualize landslide hazards on a map has been a critical advancement in understanding and mitigating their risks. Early cartographers, limited by technology, could only provide rudimentary depictions of landslide-prone areas. However, as mapping techniques advanced, so too did our ability to identify and delineate areas susceptible to landslides. The development of aerial photography in the early 20th century revolutionized landslide mapping. For the first time, scientists and engineers could obtain a bird's-eye view of vast landscapes, revealing patterns of past landslides and geomorphic features indicative of instability. Aerial photographs allowed for the creation of detailed landslide inventory maps, documenting the location, extent, and type of landslides over large areas. The latter half of the 20th century saw the advent of remote sensing technologies such as satellite imagery and LiDAR, light detection and ranging, which further enhanced our ability to map and monitor landslides. Satellite imagery, with its ability to cover vast areas repeatedly, proved invaluable for tracking changes in landslide activity over time. LiDAR, which uses laser pulses to create highly accurate three-dimensional terrain models, enabled the identification of subtle topographic features associated with landslide-prone slopes. Today, geographic information systems, GIS, have become essential tools for landslide hazard mapping and risk assessment. GIS integrates various data layers, including topographic maps, geological maps, landslide inventories, and remote sensing data to create comprehensive maps that depict landslide susceptibility, hazard, and risk. These maps are crucial for land use planning, infrastructure development, and emergency response. The study of landslides has experienced a technological renaissance in recent decades, with advancements in computing power, sensor technology, and modeling techniques. Today, researchers employ a sophisticated arsenal of tools to investigate landslides, from microscopic analysis of soil particles to satellite-based monitoring of entire mountain ranges. One of the most transformative technologies has been the development of high-resolution, ground-based sensors. These instruments, such as inclinometers, piezometers, and extensometers, can be installed on slopes or within boreholes to continuously monitor minute movements, pore water pressure changes, and ground vibrations. The data collected provide real-time insights into the stability of slopes and can be used to detect early warning signs of impending landslides. Numerical modeling has also become an indispensable tool for understanding landslide processes and predicting their behavior. Using powerful computers, scientists can create complex simulations that incorporate factors like slope geometry, soil properties, rainfall patterns, and seismic activity. These models help researchers explore different landslide scenarios, assess the effectiveness of mitigation measures, and develop early warning systems. Furthermore, the rise of unmanned aerial vehicles, UAVs, or drones, has provided landslide scientists with unprecedented access to hazardous and difficult-to-reach areas. Equipped with high-resolution cameras and LiDAR sensors, drones can rapidly collect detailed data on landslide morphology, vegetation cover, and surface displacement. This information is critical for assessing landslide damage, mapping debris flows, and monitoring post-landslide recovery.